for several reasons. So one of the reasons is that because of this phenomenon that we'll see in a minute, linear programming, kind of one of the reasons in the background why we can solve linear programming quite fast using the simplex method. So it's quite easy to find the optimal solution compared to problems that are not linear and not convex, and other problems that there are in optimization. So that's one philosophical reason almost why it's important. We won't talk much about that. But the other reason is because we'll be using it for some of the post-optimality things. So if you want to do, if you solve your problem, like creating components as the lab problem or the assignment problem, then what you get is the optimal solution, and you know how much you should do and what you should do, and that's the solution. You know the values for the decision variables. But there is actually more information that is available to you than just the optimal solution, because there is, as you will see, the dual solution, and that has a meaning. So it is somehow giving you an additional amount of information. And we'll see that in quite a bit of detail later. So just for now, just trust me that it's important. And the idea of duality is that you try, if you want to, well, so I think that we did this example in decision maths, but I'm not assuming that anybody remembers. But the idea is we want to come up with some, as it says, good upper bound on the objective. So this example is the example with the chess sets that we had in the first year. Does that ring a bell? So Z, the thing that we're trying to maximize is the profit. Okay? And so one could ask the question whether, for example, so an upper bound is something, is a limit that it cannot be higher than. Okay, so for example, can Z ever be greater than 1,240? Okay, so maybe somebody's interested in making at least £1,240 per week. Okay? So without solving everything, I mean, it's quite easy to solve for this one, but without solving anything, can you answer the question whether the Z can be more than 1,240? Probably cannot. Any ideas? Well, I have an idea. So if you just multiply this last constraint by 40, okay, what are you going to get? Well, you're going to get 20x1 plus 20x2 is less than or equal to 1,240. Does that give us any information? Important with respect to that question. Look at this. You're trying to see when you take 15 times x1 and 20 times x2, what is the largest value you can get? Okay. You know that 20 times x1 plus 20 times x2 can never be larger than this number. But then, because x1 is non-negative, this is even less than that. Well, definitely not more than that. Okay? So 20 times x1 plus 20 times x2 is definitely no less than 15 times x1 plus 20 x2. All right? And this is Z. So no. No more than this is possible. That make sense? But it doesn't make sense because we're making it more advanced now. All right. Now the question is this, well, can we do a better bound than 1240? So how about we take this times 27? Well, that won't work because then we only get 13.5 x1. And 15 is more than 13.5, so just taking 27 times this, or even 13.5, yeah. So that's not going to work. So how about we take this and then also 8 times this constraint and add them together. So oh no, I don't want 8 times, so that goes away. I want just 2 times this. So what is this giving us? Again, this is 31 over 2 x1 plus 27 halves and 8 is 1643 over 2. And this should be 1237. In my notes, so I didn't calculate it so quickly in my head. But again, this is 15x1. 15 is less than 31 over 2, and 20 is less than 43 over 2. So whatever the optimum solution is going to be, the objective is certainly not going to be larger than this number. Makes sense? Okay. The problem means I'm trying to find values, x1 and x2, that satisfy all these inequalities. Okay? And among all these values for x1 and x2, I'm trying to find the values for which this is as large as possible. Now, what I'm trying to do is, without solving it, we know how to solve it, but without solving it, what I'm trying to do is see how small the objective is going to be in the optimal solution. So I'm trying to push it as low as possible by just taking multiples of the constraints and combining them together and getting something that gives me a bound. This is a bound because, well, because z is this, and 15 is less than that, and 20 is less than that. So this bound here. And this is what we got by having the inequality. Okay? They're clear now. So this is anyway, so yeah, so the question here is, what is the best thing we can get in this way? What is the best thing we can get in this way? So how do we do it? We take some multiple of each of the constraints. So let's say we'll take a number y1 times the first constraint by y1, the second one with y2, and the third one with y3, and we add them all together, and that's going to give us a bound. Okay? So what we're going to get is Okay, 3y1 plus y2 plus 1/2 y3. This is what, when we add them all together, this is what the coefficient of x1 is going to be. And 2y1 plus 4y2 plus 1/2 y3. This is what the coefficient of x2 is going to be when we add them together. And the right-hand side is going to be 160y1 plus 200y2 plus 31y3. Okay, so this is just now we would want this to be an upper bound. So the objective is z, which is 15x1 plus 20x2. How did we make sure that this red inequality that was in the previous two cases?
We also had more x1s and x2s, so we did that.
But I always had that whatever is in this bracket is at least 20. And whatever is in this bracket is at least 50. So what I want is that 3y1 plus y2 plus 1/2 y3 is at least 15, and 2y1 plus 4y2 is it, plus 1/2 y3 is at least 20. Now this other sign. Do I need anything for this to be true? No? No? You sure? So if I did y1 equal to -2, what will it do?
Well, that would flip the inequality.
That would flip the inequality. And when we add them together, it wouldn't work anymore, would it? So what do I want? I want all these numbers to be on negative fraction. So in order for the second inequality to be true, I want all these three numbers to be greater than or equal to 0. And how about this best? What does that mean?
So inequalities 3y1 plus y2 should be
kind of intuitively, yes. There's a more obvious thing that best means. So I want forget the bits in the middle. This is an inequality that tells me that the objective cannot be larger than this expression. So, I want this expression to be small or big, or bound to be best. Big. Now the small as possible. But if this is big, if it's like 20 million, then it's not telling me much. But if this is, I can make this 1,000, then it's telling me that the objective is. So if I have one possible value of 2 million and another one of 1,000, 1,000 is better because it's more pressing. Okay? That one is small. Okay? So as small as possible, it means I want to minimize. I want to minimize 160 times y1 plus 200 y2 plus 31 y3. And so this want, now these are the constraints. So I can write subject to the constraints. What's this called? A linear programming problem. There's a linear objective. I want to minimize and maximize. Minimize and maximize. Something that's a linear function of the decision variables. And then there are inequalities. There are linear inequalities. So this is a variation because now we have two different LP problems. This one and that one. Yes. And this is called the dual. You start with one, you get called the dual. The word dual is from Latin, I think, like something with two involved. And the reason there's two is that if you started with this one and try to get the best bound on this in a similar fashion, what you would get is that. Okay. If you multiply this constrained by x1, this constrained by x2, and then you want them non-negative because you don't want the sign split. This time you want to make it as large as possible because it's going to be a lower bound. So you want to maximize, and yeah, it all works out. Okay. So you start with this one and do dualization, you get that one. You start with this one, do dualization, you get this one. So they really come in pairs. An important observation. So they come in pairs. What happens when we solve this is we get 1160. Now, what is a coincidence? Well, so this 1160 is the same as the maximum Z from the first LP. You recall that. So the optimal solution is different because there we had, oh, I can't remember. We had some values for the x1 and x2, and I can't remember what they were, but the objective was 160, and this one we solve when we get to different values for the y's. Of course, they're different, 3 y's or 2 x's and so on. But the objective is the same. And I can give away that it's not a coincidence. It's always the same. Okay, but what is it? I'm being too vague. Okay, so the two dual LP problems always have the same value, same optimal value of the objective. This solution also answers the unasked question how I came up with the numbers I used. What was it? I said twice this and 27 times that. So 27 is about 3, a little bit more, and 2 is a bit more than 5 over 3. So I took this solution first, and then I came up with 27 and 2 as the multiples for the second midpoint. So the right ones were not 27 and 2, but the right ones were 0 times the first constraint, divided over 3 times the second constraint, and over 80 over 3 times. Yeah, so it was 0 times the first constraint, divided over 3 times the second constraint, times the third one. Much time. So much time left. Okay, so now, for now, this is just my promise. I haven't told you why it's true, but I will tell you why it's true next week. But what's the next slide on in matrix form? So it's the same that I have now. Okay. Recall we did this. Instead of writing the numbers, we can use matrices and vectors. Now, if you want to get the dual, so what do? So you have to multiply. So when you, it's something that you have to think about on your own, in your own time. So what happens is, you have your note, or it's maybe, even if it's not in the note, you can see. The second page, you have the dual. On the first page, you have what I call the final. So you can compare them. So you can see where there, when you look at it, you see that what was the objective function, 15 and 20, the numbers in it, they become the constraints in the dual. Okay, so they're here. Transpose. Okay, this was a row vector, now column. And what were the right-hand sides there? 160 to 131. They're now in the objective. Again, I have to make the column a row. But that's just the transposition here. And then when you look at what happens to the numbers, maybe I should show it. So the numbers were 3, 2, 1, 4, and 1/2, 1/2 in the 3 constraints. Right. And when you look at the dual one, you see that the coefficients there are 3, 1, 1/2 in the first constraint, and 2, 4, 1/2 in the second one. Okay. So this is just this matrix A transposed. Gives you the constraints in the dual. try to digest it. You digesting? Yeah. Kind of hard to tell what's going on because everybody's just sat there. Probably after lunch, the stomach is using more energy than the brain. That's the result we get. So I don't know whether it's completely clear and everybody's like, yeah, or whether it's completely unclear. I'm lost. No idea. No.